Okay, good morning, everybody. Welcome back. Today we start developing our third fundamental principle, and we've actually been working up to it a little bit by talking about rotational energy. This is the angular momentum principle, and it's similar to our two other fundamental principles, but somewhat different. And it's going to look something like this. So let's review a little bit where we've gotten to with fundamental principles. So remember that a fundamental principle is fundamental because it applies to any system in any situation, no matter how big, how small, whatever. So we have fundamental principles. We have the momentum principle, which we've written in various ways. The momentum is short time in the future of a system, and it's very important that we pick a system, is equal to the momentum now at this instant, plus the net force acting on that system due to the surroundings, multiplied by the time, the length of time the force acts. So that's the update form. There are other ways to write it. We can write the change of momentum of a system plus the change of momentum of the surroundings is equal to 0. But in all cases, we've got this change in a quantity, in this case momentum, and then there's some input from the surroundings, which can be positive or negative. And momentum is a vector. Of course, it has a direction and not just a magnitude. And it looked like maybe we needed to review that a little bit, given some of the answers we got last time. We have the energy principle, which really looks similar in form. The energy of a system in some final state is equal to its total energy in its initial state plus inputs from the surroundings, which can be mechanical work. It can be energy transfer due to a temperature difference. There can be other things, electromagnetic radiation and whatnot. So but it still has this same form of the change in energy is equal to inputs from the surroundings. And we have change of energy of a system plus change of energy of the surroundings is 0, and energy is a scalar, which makes it easier. And today we're going to start talking about our third fundamental quantity, which is going to be called angular momentum. Angular momentum. And in its most general form, so it looks a little bit more, there's more decorations in this principle. So angular momentum is a vector. And so it's going to be angular momentum of some system a short time in the future is the angular momentum of the system at this instant plus inputs from the surroundings. And that input from the surroundings is actually represented by a Greek letter tau. But there's another thing that goes in this equation. Angular momentum, it turns out, has a subscript indicating a location about which it's calculated. So this is angular momentum. This is a location. This is a thing called torque, which means a twist. and our old friend delta t is still our old friend delta t. And of course, we can write change in angular momentum of the system plus change in angular momentum of the surroundings is equal to 0 again. And this is the form of these principles we were basically using when we were talking about collisions, and we'll see that this can apply to collisions too. So our agenda for today is mostly to figure out what is angular momentum and why is it interesting and how do we calculate it, and then we're going to have to figure out what torque is and how that modifies angular momentum and how we calculate that. So that's our agenda for today, for the next couple of days. So the motivation for this, for angular momentum, is, I think, will be sort of clear. Let's here, no, yep, that one. So here's a VPython program, and it shows a Ferris wheel like you'd ride on at a state fair, a big wheel with passengers riding around on it. And we're going to focus on this blue passenger here. And let's see. So the wheel turns and the passenger goes around. And the wheel's turning at constant speed, and this blue passenger is going around at constant speed, right? Well, lots of things are changing in this motion. So the position of the passenger relative to the point around which it's rotating is changing. So that's not constant. The momentum of this passenger is also not constant, even though the magnitude is the same, the direction is changing. So neither of those things is constant, and yet it feels like there's something important that's constant in this motion here that we ought to be able to capture. And that something that we want to capture is angular momentum. And even though the position is changing, the r vector is changing, and the momentum is changing, this p vector is changing, there's some things about their relationship that aren't changing. In particular, in this particular example, the magnitude of r is constant, and the magnitude of p is constant, and the angle between them is also constant. So it might be that if we had some quantity that was that involved the magnitude of r and the magnitude of p and something about the angle, some function of the angle between them, we'd have a quantity that would actually remain constant in this situation. Now the angle between them is 90 degrees. And 90 degrees, so if we use cosine, we're going to get a 0, and that's not going to be helpful. But maybe if we use sine, so magnitude of r, magnitude of p, something like the sine of the angle between them, that might actually give us a quantity that might be something that's constant in this situation. Now, of course, not all orbits are circular orbits at constant speed. So let's see. So you've certainly seen elliptical orbits. In fact, from your experimentation, I assume you realized that elliptical orbits are much easier to get. There's a lot more initial conditions that produce an elliptical orbit than produce a circular orbit. And so here the magnitude of R is changing, and the magnitude of momentum is changing, and the angle between them is changing. And yet, as the magnitude of P gets smaller, the magnitude of R gets larger. And it seems possible that even in this orbit, the product of the magnitude of R times the magnitude of the momentum times the sine of the angle between them would actually be a quantity that we can use. So that would give us a scalar, but there's which is a fair amount of information, but there is a problem here because there are two possible directions this orbit could be in. It could be going counterclockwise like it is now, or it could be going clockwise the other direction. And it's going to turn out to be important to be able to specify the direction of revolution too. And clockwise and counterclockwise are kind of awkward because you have to orient things in such a way that it's facing you like a clock face. And so we're going to try to get a slightly more precise mathematical definition of that. But that's basically where we're going with this. We're trying to develop a quantity here that captures this idea that something, even though momentum is changing and position is changing, there's something that might not be changing in an orbit situation like this. And this thing, not surprisingly, is called angular momentum. Right, so Seth's question was a good one. Is it just parallax that the angles don't look like a 90-degree angle all the time? They weren't, okay? And you can see this by just drawing. So in that elliptical orbit here, we have an elliptical orbit. And so here's our orbiting object. Its momentum is like this, and we were measuring R from the center of the star or whatever it was here in that orbit. And it's certainly a right angle there, but when it's here and its momentum is tangent to the orbit, we can see that that's absolutely not a right angle. Okay, so in fact your guess is geometrically right, Seth, that it would only stay, the angle would only be guaranteed to be 90 degrees in a circular orbit. So we only get, now here in this elliptical orbit, it's 90 degrees twice, right? It's, okay, well so we're gonna need to worry about defining what's the angle, right? So let's consider, so here it's speeding up and we've got this acute angle here. Here in this situation, its momentum is going to be like that, and so here we do indeed have an angle that's greater than 90 degrees. So the angle is going to vary in elliptical orbits. So it isn't a completely simple relationship, is it? But tentatively, we'll say that the magnitude of angular momentum here involves the magnitude of this vector r from a location we've chosen. And we typically call this locate, we have to give this location some name. So typically in the book, we've been calling this location A. So this is the angular momentum with respect to location A. And so this is the position vector with respect to A times the magnitude of the momentum times the sine of the angle between them. And okay, so that's our angle. But we also have to specify a direction. So this is a magnitude. But what about a direction? So how do we specify the direction of the orbit? So we could have two different situations here. So we could have an orbit that's going counterclockwise in this plane, or we could have an orbit that's going clockwise in this plane. And in order to specify what counterclockwise and clockwise mean, you have to specify the plane, right? And actually, it turns out that the easiest way mathematically is to specify a plane, is to just draw a vector perpendicular to the plane. So to define a plane. So if I tell you that this perpendicular vector is along the y-axis, you know immediately I'm talking about the xz plane. If it's the xy plane, then the vector in the z. And we still need a direction. We need a convention for direction, and that convention is given by something called a right-hand rule. So we say that an orbit in, let's say this is the xz plane, an orbit in the xz plane is specified as going up in the plus y direction if it's clockwise, and it's actually going to go down. So this is plus y and this is a minus y. If it's going, up if it's counterclockwise, down if it's clockwise, okay? And this is actually, the way you do this is to actually use your right hand. And so this is the first piece of what we're calling the right-hand rule here. So here's a picture of how you would get the angular momentum of something traveling in the purple plane showed here. So if you curl your fingers like this hand is doing, if you curl your fingers around in the direction of the orbit of your right, now you have to use your right hand. So that means if you're right-handed, you have to put your pencil down in order to do that. And that is the most common source of errors in figuring out directions, is that right-handed people forget to put their pencils down. If you're left-handed, you've got it made because you don't have to put your pencil down. But so you curl your fingers around in the direction of the orbit, and then you stick your thumb up, and your thumb points in the direction of L. And you can see that here in this figure from the book, it's labeled L hat translational. And that means that this is a piece of the angular momentum that has to do with motion of the center of mass of an object, right? And so that's pointing away from, it's pointing up. If the thing were going the other direction clockwise, you'd have to turn your hand over. So there's a lot of turning your hand over in this situation. And you see that your thumb points down, so that direction of angular momentum is that way. And so angular momentum actually is a vector, and the magnitude is given by this calculation. And the direction is given by this right-hand rule of using your right hand. Now, this is actually the direction, this is the same direction as the angular velocity of this object. So angular speed is radians per second, but angular velocity has a direction that's calculated exactly the same way. So this thing is going around with some number of radians per second, and the direction of its angular momentum is given as, if this is the, we're going to say this is the xz plane, then the direction would be plus y here and minus y there. Now, directions are extremely important, and it's really important, even though there are, we have a way to calculate a magnitude. It's extremely important to get directions right, because in some processes, the direction of angular momentum could actually reverse. I mean, something could change it. So it was going one way and then it was going the other way, and you'd have to be able to capture that mathematically. So it's extremely important to get directions right. So we're actually going to do a lot of practicing with directions today. So here is a question, a practice question for this, and it says we have a planet orbiting a star. We've got a circular orbit in the XY plane. Its instantaneous momentum is shown by that red arrow here. And the question is, what is the direction of the angular momentum of the planet? So most of you said that the direction is out of the page, and that's correct. So if you take your right hand and you just curl your fingers around so that they're wrapping around in the direction of this circular orbit. Yeah, so Joseph, most screws have right hand threads, right? So they do work this way. So so if you wrap your fingers around in the direction of the orbit, then your thumb sticks out of the page. So out of the page is right. If you said the angular momentum is the same direction as the momentum, that's completely wrong. Okay, so it's not. It's a more, angular momentum is a much more abstract idea than momentum. Okay, and this idea that it's got this vector direction basically perpendicular to the plane of the orbit, and that we've crammed a lot of information in there that tells us what direction it's going and what plane it's orbiting in. So it is indeed out of the page. So now we're using, we've changed the question to be a more mathematical kind of question here. And we're asking, if the planet is orbiting in the XY plane in the direction shown, if we have planet orbiting in the XY plane, what is the direction of, in the direction shown? So you have to look at the red arrow in the picture. So almost everybody said minus z, which is indeed correct. So if we curl our fingers around so they're following the orbit, then our thumb sticks into the screen here, and according to our axis system, that is indeed the minus z direction. Now notice that really, although there's 7 alternatives here, there's really actually in this case only 2, because the angular momentum is going to be perpendicular to the plane of the orbit. And so if the plane is the XY plane, then the only directions that are perpendicular are plus z or minus z. So you're down to 2 alternatives. And you can just, that makes your life somewhat easier. Okay, so we have one way to calculate angular momentum now. So the angular momentum is the magnitude, is just the magnitude of r times the magnitude of p times the sine of the angle theta between them, and we get the direction from the right-hand rule. But we don't always know the angle, and sometimes it's annoying to calculate it. So actually there is a mathematical way of calculating angular momentum. It's called a vector cross product. So we have the vector L is, this is a new way of combining vectors. And remember, we had one way of combining vectors that was a dot product, and that gave us a scalar. Well, this is a way of combining vectors that gives the result, gives us a vector. So what does a vector cross product look like? Well, it helps to look at it in VPython. So let's share the screen. Okay, so this is a visualization of the vector cross product here. So the cross product we're calculating is that, and cross product, it turns out, so in this case, the yellow vector is red cross green. Now it turns out cross products are, the order matters. So green cross red is not the same as red cross green. And let's see what this looks like. So we can change, the red vector is fixed here, but we can change the green one. So first of all, the magnitude of the vector matters. And second, the angle matters, so that it turns out when these vectors are exactly 180 degrees from each other, when this angle between them is 180 degrees, the vector cross product comes out to be 0. And that's true. You can see that from the equation for the magnitude too, because magnitude of the sine of theta here is now 0. And presumably it should also be 0 if they're in exactly the same direction. And that's true, it's 0 here. It's a maximum when they're at right angles to each other. And it's okay. And it can change direction. So notice that in this first, when the angle here in the first quadrant is so we've got angle less than pi over 2, we go to pi, and now it's 0. And now if we keep going, the result is in the other direction. Okay. And this is a demo program you can play with if you want to. So if you we've fixed the length of the green arrow, and all we're doing is varying the angle, and you can just see the effective angle without worrying about effective length. Or you can lock the angle, and then all you can do is vary the length and see what happens here in this. So this is a possibly useful program to play with. So that's so it's clear that computationally this is a good way to calculate it, and let's see what's going on in this computational calculation here. So so basically what we're going to need a vector cross product the result is going to be a vector that's perpendicular to our two vectors. And notice that to measure the angle here, we put these vectors tail to tail, just like we do when we're subtracting vectors. So if we have some vector A and some vector B, to get this angle, we put them tail to tail to get this angle theta. So in its most general form, the A cross B, vector A cross vector B, and again, order matters, is going to give us a vector with three components: an X component, a Y component, and a Z component. And they're going to look like this. So the X component is A sub Y times B sub Z minus A sub Z times B sub Y. So that's, if that's a vector C, this is C sub X. And the Y component is AZ BX minus AX BZ. So that would be C sub Y. And the Z component is AX BY minus AY BX. Now that looks like a lot of calculations, and it is a lot of calculation by hand, except for the fact that you really only have to do one of these. Because usually, I mean, if it's in some obvious plane, so if it's in the XY plane, if the orbit is in the XY plane, you know that the result is going to be in the plus or minus Z direction. So all you'd have to worry about would be that. Now, how do you remember this order? Well, it's, notice that the X component involves Y and then Z. The Y component involves Z and then X, and the Z component involves X and then Y. So it's, if you write, some people write XYZ, XYZ, and so the X component is Y and Z, then the Y component is Z and X, and the Z component would be X and Y, starting in that order. Yeah, so VPython is your friend because VPython will do it for you, of course. And so in VPython, we just have C equals cross A comma B, but that's what it's doing. Okay, so this is what it's doing. So R cross P, which is what angular momentum actually is going to be equal to R sub Y P sub Z minus RZ P Y and RZ PX minus RX PZ and RX PY minus RY PX. Why is it given the letter L? I don't know. I don't even know if there's a word in any language for angular momentum that starts with the letter L, but why is momentum P? Okay, I think it might have been something from Latin there. Now, in general, for a general, yes, the letter L. So the general approach to finding a direction for angular momentum, if you have two vectors here, is basically to use your right hand, but in a very slightly different way than we did for something where we knew a whole orbit. So if we just instantaneously know the two vectors here, we can use our right hand to actually get a direction. So we're going to want R cross P. So the first step here, again, a figure from the textbook, is to draw these two vectors tail to tail. So the first step is draw them tail to tail. The second step is to use your right hand, and you point your fingers along. In this case, it's R in general. It's vector number 1. If you do it backwards, you're going to get the wrong sign. So here you can see in step 1 in this figure that the person has drawn R and P with their tails together, and now they're aligning their hand along R. Now this aligning your hand in doing a vector cross product this way, it's very important that you keep your wrist straight, so no floppy wrists. We have the karate hand here, or think of your wrist being in a cast or something. So you've got your wrist is straight. And then once you've aligned your fingers with R, you curl them, you bend them toward P. So as if you're kind of folding R into P, okay? And having done that, your thumb sticks up in the direction of L. Now, so that's straightforward. If you're one of these people who really doesn't want to take your hand out of your pocket, you're going to suffer in this topic. You really have to actually be willing to put down your pencil, take out your right hand, and you may have to move your paper to do this. There is, however, another thing to worry about here, and I'm going to use the other camera for a minute here because I have a thing to show you. So here is here's two vectors. We have, let's say the blue one is R and the orange one is P. And we want to take a cross product. We want to know the direction of the cross product. So what we're going to do is we're going to line up our hand with R and then try to curl our fingers toward P. Except that the way I've done it here, I can't do it without breaking my fingers. We're always curling them through the smaller angle. Okay, so I'm not going around like that. And I can't do this without breaking my fingers. So what I actually have to do is turn my hand over. Okay, so you may find that when you're trying to take a cross product, it doesn't work. And what you have to do is just turn your hand over. And that's why this right hand thing works. Now I can curl my fingers from R to P, and now my thumb is going to stick into the page, which tells me that the direction of that R cross P is into the page. Okay, so there's definitely going to be some rotating wrists. And also, there may be situations where you just actually want to rotate the paper. So you want to redraw it and rotate the paper. So now you need to be able to calculate, to determine cross products both ways. Okay, magnitude of P, sine theta, and right hand rule to get the direction, or use the full formalism for the vector cross product to get this. So let us practice a little more. We're going to do a lot of practicing today on this because it's actually really important. Okay, so again, anything we spend this much time on is actually important. Here's a question. What is the direction of the cross product 003 cross 040? Okay, so particularly good news is that most of you realize that because these vectors, one is in the plus z direction and one is in the plus y direction, then the two vectors lie in the YZ plane, so therefore the only possible perpendicular directions are plus or minus x. So then the question is, what is the direction? And the answer is indeed minus x. So I actually did this by turning around and saying, okay, if my fingers are pointing in the first one is in the plus z direction, so I'm going to point my fingers in the plus z direction, then I'm going to curl them in the plus y direction and point my fingers in the minus x direction. So I actually was imagining coordinate systems and using my hand to do that. We could also, of course, just work it out because so we know it's the x component that we care about, and so remember that so x component would be AYBZ minus AZBY, so that would be 0 times 4 minus 0 times 0 minus 3 times 4, so it's going to be in the negative x direction. So what would the answer be if we reverse the order of these vectors in the cross product? So before we did 003 cross 040, what would the answer be if we said 040 cross 003? Okay, so the overwhelming answer is plus x, and that's correct. So we have y cross z definitely is in the plus x direction. And so you can see that the order of the vectors in the cross product makes a big difference. You got to get it right. Let's just do a couple examples of actually working out angular momentum. So, and we'll do one using each of two methods. So here's our example. The magnitude of momentum of an object is 20 meters per second. And it is a distance of 5 meters from location A. So here is our diagram. We have an object moving with some momentum P. And we have a location A here. And so that's our R, and the sub A just means R, having picked A is the location around which we're going to calculate angular momentum. And this angle is 30 degrees. So we can calculate, so here we're going to use magnitude of r, magnitude of p, sine theta, and then get the direction from the right-hand rule. Okay. So the magnitude of L with respect to location A is the magnitude of R, which is 5 meters, times the magnitude of P, which is 20 kilogram meters per second. Kilogram meters per second. Times the sine of the angle between them. What is the angle between them? Well, we kind of need to put them tail to tail to tell. So if we just extend this line here, we can imagine taking r sub a and moving it up here, just redrawing it up here. Oops. So redrawing it up there, and that angle is clearly also 30 degrees. So it's sine of 30 degrees, which is going to give us 50 kilogram meters squared per second. So it looks like the units of angular momentum, we're multiplying meters by kilogram meters per second, so the units must be kilogram meters squared per second. And we can get the direction by, here it's sort of easy, we align our wrist with R, and then we can curl our fingers toward P, and our thumb sticks out toward us, and so the direction is going to be the plus C direction. So we would write the answer, as we can now write the answer as a vector. We can say LA is going to be 0, 0, 50 kilogram meters squared per second. Right? So here's a different example. Suppose we have an object with momentum like that, and we still have a location A here, so this is R sub A. And now what we know is we know the values of the vectors. So we know that the momentum is 0, 30, 0 kilogram meters per second. And we know that R is equal to negative 530 meters. And so we want the angular momentum around location A is going to be R sub A cross P. And here it's actually easiest just to use the full formula rather than trying to figure out an angle. So L sub A is going to be equal to, so the x component is RYPZ. So this is 30 times 0 minus, RYPZ. So 3 times 0 minus PY times RZ, so that looks like a 0. And the y component is going to be RZPY, so that's 0 times 0 minus RYPZ, which is, the y component, let's go back. We want Rx RZPX minus RXPZ. So we want 0 times a -5, 0 times 0 minus 5 times -5 times 0. And finally, we want for the z component RXPY minus RYPX. So that's going to be 0 times a -5 minus 3 times, wait, this is RXPY, -5 times 30 minus 3 times 0. And so we get 0, 0, -150 kilogram meter squared per second. And is that the right direction? Well, we can check with our hand. So if we put these two, if we move this R vector so it's up here, we curl our fingers from R to P, our thumb sticks into the board, so it looks like -z direction. So I think the message here is that it helps to write out the formula before you start plugging things into it. Okay. So notice that, so in a computer program, for example, in an orbit program that you wrote, at any instant, you know the momentum of the object and you know its position relative to. Okay, so what does point A represent? So you know its position relative to point A. What does point A represent? Point A is actually an arbitrary location, except that we aren't going to be choosing it to be arbitrary necessarily. And let me show you in a VPython program what this actually means. So that's an important question. So let's look at VPython here. Okay, so here's our elliptical orbit. Okay, and here we've taken the location A to be the center of this, probably looks like the sun. This looks like a comet going around the sun, right? We've taken it to be, so we're drawing that, and momentum is just momentum, right? So that doesn't, but if we, so that's location A, and if we actually show the angular momentum around that location in this system, it's actually constant. So the angular momentum of the comet going around the center of the sun is actually, if we pick a different location, it's actually not a constant. So it's going to turn out that what choosing location A is involved with is this last piece of the angular momentum principle, which has to do with the change in angular momentum being due to a torque or a twist exerted by something. And But when you have a twist, you have to have a twist around something. So what that place you have a twist around is the place. Now, normally when we calculate angular momentum, we're actually going to make probably the obvious choice. Okay, we're going to calculate it around something that looks like the center of where something's going around. We don't have to do that. But we do have to pick a place. So that's basically the point of this location A thing. Now, it's actually true, and it turns out to be physically even relevant, that we can calculate the angular momentum relative to some location of something that's actually not going around. It's even traveling in a straight line. So here's a situation where we have a ball falling straight down. Its momentum is shown by the red arrow. We have the usual coordinate system. And the question is, if we take the origin here, the location A, the origin is location A. If we just calculate the angular momentum using the expression for angular momentum, you know, R cross P, what direction are we going to get? And then we'll see if this makes any sense. Okay, Alexander, so that's the right question, and we should get there after this. So what's the point? So things not changing, so what's the point? So we spent a lot of time figuring out how to calculate this without talking about how it changes, and that's where we need to get to. Okay, let's see what y'all said. Okay, so we have, well, I wouldn't call that great. Okay, so most of you figured out that it was either in the plus or minus z direction because we're talking about the xy plane here. It is not 0, interestingly, and if you answered 0, I think you're guessing and not calculating it. So let's actually see what the direction is, and then we'll see why this matters. So let's draw. So we have to draw a vector r here. So r goes from location A to the ball, and we have our vector p here. And now we need to put these tail to tail. So we have r and p. And so here's the angle between them. So if we point our fingers along r, curl towards p, our thumb sticks into the page. In fact, it has angular momentum in the minus z direction. So the magnitude is not 0. And this makes sense for the following reason. So back to VPython here. So here we have a thing that can rotate. And we have so it's a bunch of balls, massive balls on very low mass spokes. And here's a lump of clay that we can drop onto it. So this lump of clay starts out, so initially the wheel is at rest. So this wheel essentially has no angular momentum. Now, how do we calculate the angular momentum of the wheel? Well, we calculate it by adding up the angular momentum of each of the pieces of the wheel, right? If we drop the clay onto the wheel, then the wheel actually might start to turn. And if we pick our system as the clay plus the wheel and nothing interesting in the surroundings, then the angular momentum of the system shouldn't have changed. This is a collision, basically, right? So in collisions, when we talked about collisions, we looked at energy and we looked at momentum, but we also need to think about angular momentum. And the fact that this thing is the falling ball, which didn't look like it was going around anything, nonetheless seems to have imparted angular momentum to this wheel. And if we drop the ball in a slightly different location, it makes it spin a little bit less. And if we drop it right along the center, it doesn't do anything. And if we drop it over here, it makes it turn to the right. So now it seems to have angular momentum into this screen. And if we drop it over here, it has even more angular momentum into the screen. So here's a situation where the angular momentum of the wheel changed. And there are two ways to think about it. One, the ball exerted a torque, or two, if we take the ball plus the angular momentum, plus the wheel as the system, the angular momentum of this whole system must have been constant. And so it was the angular momentum of the falling ball that now is the angular momentum of the whole system. So this gives us an insight into collisions where we can actually look at what happens to internal energy and angular momentum in a collision. Now, another important thing about angular momentum is that, just like momentum, you need a force to change momentum. Well, you need a torque or a twist, a force relative to some location, think of a lever, to change angular momentum. And this shows up, this actually shows up in a lot of situations. If you've taken chemistry, you've probably talked about different kinds of orbitals, p and d orbitals. Well, in those orbitals, the electrons moving around the nucleus actually have angular momentum with respect to the nucleus. And so it's called orbital angular momentum. We'd call it translational angular momentum here, relative to the nucleus. And to change that angular momentum, you actually have to apply some kind of twist. It turns out, we'll see, we'll do a little bit maybe this time, but next time we'll talk about angular momentum of not just single particles going around, but objects rotating, like angular momentum of this wheel or angular momentum of a solid wheel or something like that. To change angular momentum, you have to do something. You have to apply a torque. And it turns out that things like electrons and actually protons in the nucleus actually have angular momentum due to just spinning on their own axes, essentially. And to change that, you have to apply a force. Well, how can you apply a force? Well, it turns out you can do that with a torque, rather. You can apply that with a magnetic field. And flipping the angular momentum of a proton is how you do magnetic resonance, fMRI. That's, you're looking at flipping angular momentum of nuclei. If you're doing NMR studies of chemical compounds to characterize them, you're actually applying forces to change the angular momentum of nucleons, of protons. So this is pervasive, and it isn't just wheels going around or planets orbiting stars. It turns out to be an important consideration in many situations. So that's exactly the right question to ask. What's the point? And next time we'll talk about calculating angular momentum of large objects, extended objects, and then we'll talk about torque and how we would apply torques and how you calculate torque and how you change angular momentum. And I wanted to go slowly today just to make sure that we really got this concept and could apply it, and you really need to practice this actually. And because if you don't know what angular momentum is, then talking about how it changes is actually not all that useful. So that's the basic message. So why is, okay, so in the practice question, why was R toward the falling object? So, well, it is because it always, R always goes to the object. The question is, where does it come from? Okay, so R is always extends from some location A to the object. The question is, where does it come from? Why do we pick A there? It was arbitrary in this case, but in the case of the clay falling onto the wheel, where do you think we would pick the location A to calculate angular momentum from in the wheel situation? Presumably in the situation of the, if we have the, here's our wheel. Okay, I'll make it simple. And here's our falling ball. It's going to rotate around here, so presumably we're gonna, yeah, absolutely, we're gonna pick the center of the wheel, right? And so that's going to be R, and that's going to be P. So Mitch, angular momentum really has a going aroundness flavor, and we'll, as we work with it, I think it'll become clear. All right, so the question to answer in chat for attendance is, what's the most important thing to take away from today's discussion? And what questions do you still have?